So last time we have seen various ways of parameterize the orientation of a body, of a rigid body in 3D space. Okay, we've seen, in fact, Euler's angle parameterization, whose advantage was mainly the use of only 3 parameters, which is the smallest number possible to be able to parameterize the rotation, the orientation of a body, but which had the drawback of falling into the gimbal lock problem, which is nothing different from a singularity problem, okay? A problem which affects typically every parameterization of the orientation of a body in space, which resort to the use of 3 independent parameters. This was the case, of course, also for Rodriguez parameters, which we have seen as well, which had, again, the problem of singularity. But that was not the case, for example, for Euler's parameters, where there the set of parameters needed to parameterize the orientation of a body was equal to 4. Now, we will move on from these concepts in order to be able to see what are the mathematical properties of the rotation matrix, which we have also named as transformation matrix, because we will see, analyzing these properties, that in fact we will have the need to be able to distinguish some features of this matrix that will be the basis, that will constitute the basis upon which building the successive treatment, mathematical treatment of the course. So, first of all, we will deal with the properties of the rotation matrix or transformation matrix. So the first property is the orthogonality of the matrix. So do you know what is the orthogonality of a matrix? Does someone of you know? Also from home, huh? Do you have any idea? So the orthogonality of a matrix holds when the inverse of a matrix is equal to its transpose. Okay, that's the definition, by definition, of the property of orthogonality. So we have to demonstrate that. In fact, there will be 2 ways by which we will be able to demonstrate this property, which is very important for the development of the formulation, because instead of doing an inverse of a matrix, which is always an operation which is always computationally intensive to do, you can do the transpose, which is much, much easier. Well, that helps a lot, okay? So this is very useful property. And as I was saying, we will be doing this, we will be demonstrating this in two different ways. The first one will be more, let's say, mathematically consistent. The second one is more intuitive. So let's demonstrate this. So first, some facts. So we have some observation. I don't know if you have noticed it, but when you deal with a skew matrix, like, for example, the V tilde that we have introduced, you have the following. So if you have v tilde squared, in the sense that basically we have v tilde applied over v tilde applied over v tilde, like this. This is v squared for us. Sorry, v to the third. Well, you can see that since v with a tilde indicates, as we have seen, a skew-symmetric matrix, well, this is equal to nothing different than v tilde with a minus. Okay, you can verify it by yourself. Then we have other things of the like. For example, we have that v tilde to the fourth is equal to minus v tilde to the second. Okay, this also is something that you can prove. Or, for example, that v tilde to the fifth is equal to v tilde. Okay, and so on. If we want to, let's say, write all these properties in a more consistent way, we can write the following. So in fact, the following holds. We have that v tilde to the 2 times n minus 1, which is basically the way we write an odd exponent for the matrix, is equal to minus 1 to the n minus 1 times v tilde. Okay. All right. And the second one is that v tilde to the second times n is equal to minus 1 n minus 1 v to the second. Okay. Okay. We will use this right now. So let's write a tilde applied over a. So resorting to the definition of given by Rodriguez formula, we have that first we have the identity matrix, and we should transpose it. But the transpose of the identity matrix is the identity matrix itself, right? Then we should have plus v transposed the sinus of theta, right? But v tilde is a skew matrix. So what's the result of the transpose of a skew matrix? Is the skew matrix itself pre-multiplied by a minus. Okay, so we can do this, and we can do this, right? Then we have 2 we should have this transposed, okay, as well. Is that correct? But the transpose of this, okay, is basically 2 times the transpose of v, right? So we could write something like this. This is the transpose of this applied over, because you know that the transpose operation distributes over a multiplication of matrices, all right? So for those of you who don't know that, these are 2 matrices, okay? And you do the transpose, right? this is nothing than B, so you have to reverse the order, transpose applied over A, transpose, okay? This holds. If you apply it here, because we have seen that V tilde square is nothing than V applied over V, okay? Then you apply the first transpose over the first V, and then over the second. Okay, you should basically reverse, but they are the same matrix, so it doesn't matter. And every time you apply this transpose, you should then, you can cancel it, this transpose, apply the minus in front, as just we have done here, okay? Like this. And so eventually nothing changes. That's the final result. If you, the transpose of the V squared is V squared, okay? So you can basically just remove this. And this must be multiplied by base 8, by A, okay? Which I will write here. So it's I. In this case, we have plus V tilde over the sinus of theta, plus 2 times V squared tilde times the sine squared of theta divided by 2. Okay. Well, if you do this, you have the following. Well, there is a little bit of algebra involved, but it's very simple. So I will sum it up for you. And you have this V squared multiplied by the sinus squared of theta plus 4 times V squared sinus squared of theta divided by 2 plus 4 times V to the 4th. Multiply the sinus to the 4th of theta divided by 2. Okay. So this is an identity matrix, like this. Now, if we apply this, we apply these properties here, we can rewrite the following. So let me just write here. We put a sign like this, and let's write, if we consider the properties here, then we can rewrite the following. It's I plus V to the 4th sinus squared of theta minus minus 4 V to the 4th sinus squared of theta divided by 2 plus 4 V to the 4th times sinus to the 4th of theta divided by 2. Okay? Now, what I do is basically apply the famous trigonometric formula to this, so that I only deal with theta divided by 2. So I do this. For V squared, so this is what I'm writing here, sinus squared of theta divided by 2 times cosinus squared of theta divided by 2 minus 4 V to the 4th. So this is what we already had, theta divided by 2 plus 4 v to the fourth sinus or to the fourth of theta divided by 2. Now, what we do now is try to group what is the common term which is this one, for v to the fourth of the sinus squared of theta divided by 2, which multiplies what? Well, we have this, and then we have this, right? So we have, if we take into account this, we have sinus squared of theta divided by 2. Then I take this one here, and then I have plus cosinus squared of theta divided by 2. And then I have a minus 1, right? This is super easy, to see that the one between rectangular brackets is 0. And so basically this eventually amounts to the identity matrix, which basically demonstrates the thesis, right? Because if A transposed applied over A is equal to I, the identity matrix, then it follows that if I multiply from the right, the left-hand side by A to the minus 1, what I get is that A transpose is equal to A to the minus 1, right? And this basically proves the thesis. So this is the most, let's say, consistent way of demonstrating it, but we have another kind of more intuitive demonstration. So which is useful to see because it makes you understand really what is the physical meaning behind this concept. So from before, or from above if you want, we have that the transpose of A was equal to, we have seen it already, it's I minus V tilde sinus of theta plus 2 times V square tilde sinus square of theta divided by 2. Okay? This we have already seen. But then A to the minus 1, when you have to think about A to the minus 1, let's think about it from a physical point of view. When you apply A to a vector R, basically you rotate it, okay? You apply the rotation theta, if theta is the name of your rotation. So if you apply A to the minus 1, physically, what do you think you're doing? You are counter-rotating. You're applying the opposite of the rotation, right? So if you apply A, let's do this. If you apply A to R0 over bar, you obtain R0, right? But then it is also true that if you apply A to the minus 1 to R0, you must be getting R0 over bar, right? That's exactly what you're talking about. If to the first writing you apply A to the minus 1, at the left-hand side you get the identity matrix, and on the right-hand side you get this one, right? So really, this really demonstrates what we were saying, that applying the inverse of the rotational matrix to a vector, it means that you're applying the opposite of the rotation. So if this is a rotation theta, okay, this is a rotation minus theta, okay. So you can say that a to the minus 1 of theta, of the angle theta, and the axis v is equal to, basically, equals to apply the rotation a of the angle minus theta, okay, always about the same axis of rotation. Okay, this is what I'm saying here. But if this is the case, then let's apply it. So a to the minus 1 means must be the, if we want to write a to the minus 1, we must write a, but instead of for a rotation theta, for a rotation minus theta. That's all, right? So let's do it. It's a. Here we have basically plus v applied over the sinus of minus theta plus 2v squared to the sinus squared of minus theta divided by 2. Well, let's rewrite it. This is super easy, as you can see. It is I. The sinus of minus theta is minus the sinus of theta, because this is it's a skew. It's an odd function. Okay, so it's minus v to the sinus of theta plus 2v squared. So the sinus squared is basically, this is now it's an even function, so it doesn't matter the sign of the argument of the function. So this is sinus squared of theta divided by 2. And this is exactly the same of the transpose, you see? Right? So this demonstrates again the argument. So this is another demonstration of the fact that really, when you talk about the inverse of a matrix, you can write it as the transpose. All right. This fact has a nice consequence, which basically leads us to the second property, okay, which we can entitle as eigenvalues or eigenvector of the transformation matrix. If we apply the transformation matrix to a vector which is parallel to the axis of rotation, what do you expect to obtain? Right? If you apply the rotation matrix to a vector which is parallel to the axis of rotation, what do you expect to get? The same axis of the same vector. So this is actually the definition of what? Of eigenvector. Right? So let's do it. Let's prove it. So first of all, let's recall that if you write this, for our convention, this is equal to what? This is equal to v vector v, right? And this is 0 by definition. Okay, the vector product of a vector with itself is 0. And also, v squared applied over v, well, it's the same, right? This is 0 as well. So we define now the vector lambda, which is something should ring a bell, as what? As we said, something which is parallel to the axis of rotation. So it's a constant c multiplying the vector, the unit vector v. Okay, so this is a constant, scalar constant. Okay. All right. Now, let's now then define A applied over lambda. A applied over lambda is the identity matrix plus V tilde sinus of theta plus 2 minus sinus squared of theta divided by 2 applied over lambda. And this can be written as what? As the scalar C, which we can group in front, times what? Well, the identity matrix over V is V itself, right? So it's V. Then we have V over V tilde applied over V sinus of theta plus 2 times V squared tilde applied over V over the sinus squared of theta divided by 2. Right? So this is 0. Right? The first one. The second one as well. So we are left with C times V, which is lambda. Okay. So we have seen that A applied over lambda is lambda. So this demonstrates that lambda is an eigenvector. And what's the eigenvalue associated to it? Do you know? Can you guess? It's 1. Exactly. Lambda is okay. All right, now briefly, another important concept. Oops. So we have seen that, especially in the case of the Euler's angles as parametrization to describe the orientation of a body in the 3D space, we have seen that the sequence of the order of the rotation that one evaluates, that one considers, in order to be able to establish the final configuration, it does matter, right? It matters. You cannot just, if you change the order of the rotation, you don't typically get the same final configuration, all right? So let's see this in an example. So successive rotations. Always for A. So let's take a look at this. You see? Now look at these two different rotation sequences. Okay, you start with the same initial configuration. So the body has the same initial position. First, in the upper row, you first rotate the body of 90 degrees about the axis x2, and then 90 degrees about the axis x3. And this is the final configuration that you get. Okay. Now, in the last row, you first rotate it by 90 degrees about x3, and then you rotate it by 90 degrees about x2. So you reverse, basically, you inverse the order of the rotation. You see that the final configuration is not quite the same. Okay. This is a very intuitive proof of the fact that the order of the rotation does matter, and the rotation operation is not commutative. Okay. If you rotate something according to a certain sequence of rotations, well, the sequence of rotation does matter, and the rotation operation is not a commutative one. Except for one case. Can you guess what it is? Il cubo? Well, if it's a sphere and you rotate it wherever, it doesn't matter. But no, that's not what I was meaning. There is a case. No, I'm not talking about the object that you initially rotate. Okay, I'm talking about a special condition for these rotations, by which, in which case, you can actually say that the rotation sequence does not matter, because the rotation is actually commutative. Anyone from home as well? The middle angle. Nope. Well, if the axes of rotation are parallel, right? If I rotate something of an angle alpha, about an axis of rotation, and then I take into account another axis of rotation, which is not the first one, but it's parallel to the first one, and I rotate it of an angle beta, eventually, if I do the opposite, I end up with the same configuration, right? Because if you think about it, I can describe it as a single rotation. That's why it's a trick. It's not really a sequence of two rotations. It's just a one rotation split into two phases, right? I rotated first of, I don't know, 90 degrees, and then of additional 30 degrees. If I rotated first 30 degrees, and then I add the 90 degrees afterward. If the axis of rotation is the same, then we have the commutative property. Otherwise, in all other cases, well, we can't do it. And well, if you take into account if you look at this, so you know what is the structure of the general eigenvalue? So, well, the A in this case, all right. The typical structure of the, for example, of the eigenproblem for the structure for the space structure in general for structures is something like this. Okay, have you ever seen this? Multiple times, right? So in this is the general expression. In our case, we do not have this because we only have one matrix, which is A. And our eigenvalue, eigenvector, sorry, is this one, okay, which is B. Now, since when you rotate the, when you apply the A matrix, so the rotation matrix over lambda over V, you obtain the V itself, okay, not multiplied by any other kind of constant other than one. Well, that's one. That's one way of saying it. Otherwise, you can basically solve this one. If you can solve this one, basically divided by k, and you have something like this. To the -1 applied over zeta n. Okay, and this is your A. And you see that basically this lambda here is 1. Yeah. That's one. That's the most general way of seeing it, but it's kind of intuitive. This is like shooting with a cannon to a bird, in our case, all right? All right, so let's actually see this one in a more mathematically consistent way. One way that we can actually describe this is the following. If you take into account, if you have a matrix C1, okay, so you can associate to this matrix another operation like this. You can do the exponent of this matrix. And this is a matrix as well, right? Now, so this is something that you can do. This is still a matrix. Now, in general, it is possible to see that if you take into account two matrices, C1 and C2, for example, then if you do E to C1 applied over E to C2, this is in general different from doing E to C2 multiplied by E to C1. So what you typically do with scalars, okay, it does not hold for matrices. This is a well-known mathematical properties. In general, you can do this. E to C1. This is in general different from E to C1 plus C2. Of course, from the first row follows the second, because if the second row was true, then the first one would follow, right? If you could write this, if this were true, then of course this would be true as well. Okay, so this is just a consequence. Why are we doing this? Because if we can exploit this fact, we can mathematically prove what we have seen here intuitively. Okay, how so? Well, we can do the following. If we write A, as we have done already, we can write it as this one. So instead of writing now 2 times the sinus squared of theta divided by 2, we can write it as minus 1 minus the cosinus of theta. This is exactly equal to 2 times sinus squared of theta divided by 2. Why did I do this? Because now we can express in series, we can expand in series the sinus and the cosinus. So we can do the following. The sinus of theta is equal to what? Is theta, and this we well know, right? This is the linear approximation that we so many times profit of. But then, in fact, there are other terms. Theta to the third divided by 3 plus theta to the fifth by 5 plus other terms. While for the cosinus, you have 1, as we know, and then we have minus theta squared divided by 2 factorial plus theta to the fourth divided by 4 factorial plus others. So that A can be written as I plus, if we substitute, we have theta minus theta to the third over 3 factorial and others, plus, and this is all multiplied by v, of course, plus, well, what we have seen before. So I substitute cosinus here, so -1, 1, they go away, plus, actually, it's actually minus, what? Plus others, times v tilde squared. Now, by definition, we have that E2 with the matrix B as an exponent is equal to identity matrix plus B plus B squared to 2 plus B to the third times 3. And we can continue. Now, if you rearrange these terms inside the matrix, you obtain this. So rearranging A, we write is exactly I plus theta scalar applied over B plus what? Theta square divided by 2 factorial applied over V tilde squared. What I'm doing here is just rearranging these terms here, which I have written here. Okay, I'm just reordering them. You see, I'm just putting this and then this and then this, right? Plus theta to the third divided by 3 factorial times V to the third, and so on. Eventually, we get theta to the n factorial to the n. But then you see, if I define this term as our b in the writing before, it means that I can write a as what? As e with an exponent equal to what? Theta scalar times v tilde. Right? Okay. So now I am really where I wanted to be. Why? Because now if I have that theta 1, A1, sorry, is equal to E, which operates over, right, theta 1, which is the angle, the first angle, for example. And then we have V1 tilde, which is the skew symmetric matrix developed starting from the first rotation axis, okay, V1. And then we have A2, which is equal to E applied over theta 2 over V tilde 2. So I consider two different angles, two different rotations, about two different axes, okay? For what we have demonstrated here, I can write A1 and A2 like this. Now, if I apply A1 over A2, you can write it like this. Theta 1 V1 tilde applied over theta 2 over v tilde 2. And this, for what we have seen, this is actually the thesis where we started from, okay? This is different from writing E theta 2 v2 applied over E to the theta 1 v1, which would be exactly what? A2 applied over A1, okay? So we have demonstrated that A1 applied over E2 is different from A2 applied over A1. And so this demonstrates that rotation are not commutative. Apart from parallel axes. If we have axes of rotation which are parallel, then it holds. Okay, we can actually write it. So this basically will help us describing what will come next. And what will come next is the way we will be able to describe successive rotations. So if we have a number of rotations, because we want to describe a complex change in the orientation of a body in the 3D space as a sequence of elementary rotations about axes which we know, how can we do this? How can we describe this succession of rotations? There are two methods, the single frame method and the multi-frame method, which we will see next time. The first one basically refers always to the same frame, which is the inertial frame. So anytime you do a rotation, then you have to bring back all the quantities to the inertial frame and then apply the new rotation. Okay, that's the first one. The second one, you do not have always to come back to the inertial frame, but you always refer to a new frame, which is the local frame of the body, which has performed the rotation. Okay, every time it is rotated, it changes the orientation, but you always consider the new local frame. Okay, and that's why it's called multiple. It's called multi-frame method. Okay, to describe succession of rotation. So this is all. I will stop the recording.